welcome to another module in this massive open online course. So, in this module let us start looking at the spectrum of the FM signal, alright. So, we are looking at frequency modulation. Let us now start looking at the spectrum of an AM signal, okay. So, we want to look at the spectrum or spectrum of FM signal. The spectrum of an FM signal, alright. Let us write our FM signal ST equals AC. Let us write this as AC cosine 2 pi FCT plus beta sine 2 pi FMT, as we have seen, where beta is our modulation index, okay. So, beta is our, this is our, we have seen this before, beta is the modulation index. Now, what I am going to do, I am going to write it as this, I can write this as the real part of AC e to the power of j 2 pi FCT times beta sine 2 pi FMT, which is equal to, well, now I can expand this as, so first I am writing AC cosine 2 pi FCT plus beta sine 2 pi FMT as the real part of AC e to the power of j 2 pi FCT plus beta sine 2 pi FMT. Now I can split this as AC e to the power of j e to the power of j beta sine 2 pi FMT times e to the power of j 2 pi FCT. And we know that whenever I write a signal in this fashion, that is real part of some signal times e to the power of j 2 pi FCT, this becomes, this is the complex baseband equivalent signal, okay. So, we know that when we have a passband signal XPT, XPT is the real part of XBT, which is a complex baseband equivalent signal times e to the power of j 2 pi FCT, okay. So, this is basically your equivalent complex baseband signal. This is the equivalent complex baseband signal. This is your equivalent complex baseband signal of the FM signal. Of the FM signal, okay. And therefore, the complex baseband signal is, well, that is your SBT equals AC e to the power of j beta sine 2 pi FMT. Now, what I can do is I can equivalently find the spectrum of the complex baseband. So, I can find the baseband spectrum, then the passband spectrum is nothing but simply a translation of the baseband spectrum, Okay. So, I am first going to find the spectrum of this complex baseband signal and basically going to translate it appropriately, because modulation is nothing but translation in the frequency domain. Okay. So, first let us start by finding the spectrum of this equivalent complex equivalent baseband FM signal. So, we will find the spectrum of this signal. We will find the spectrum of this signal. We will find the spectrum of this signal, which is basically, now if you look at this, that will be, now first look at this signal AC e to the power of j beta sin 2 pi fm t. Now realize that this signal is periodic. Okay. Sin 2 pi fm t is periodic with period, well, period is t equals 1 over fm. Naturally, sin 2 pi fmt is a periodic signal. So, e to the power of j beta sin 2 pi fmt is also a periodic signal, okay, and with the same period, with period t equal to 1 over fm. Okay. In fact, if I look at this, I look at it k periods later, I have e to the power of j beta sin 2 pi fm t plus k by fm, that is going to be e to the AC e to the power of j beta, well, sin 2 pi fm t plus 2k pi, which is nothing but AC e to the power of j, because j beta sin 2 pi fm t plus 2k pi is nothing but beta sin 2 pi fm t. So, this is simply e to the power of j 2 pi or e to the power of j beta sin 2 pi fm t, and therefore, this is periodic with period equals this is periodic with period is equal to 1 over. Therefore, now we can find the equivalent spectrum would be, now we said that whenever, remember that we have a periodic signal, the spectrum is given by the Fourier series, the discrete Fourier series. Therefore, we have to find the discrete Fourier series. Hence, spectrum will be given by, hence spectrum is given by the discrete Fourier series. In other words, I can write this signal, your SBT, which is periodic, as summation, remember the discrete Fourier series at the fundamental frequency and the harmonics, that is Cn e to the power of j 2 pi n fmt. This fm, remember we already said fm is the fundamental frequency. This is the fundamental frequency. So, I can write it in this as a linear combination, infinite summation of harmonics at fm and the at fm, that is frequencies fm and multiples of fm. Fm is the fundamental frequency, all right. This is the discrete Fourier series. This is the representation, all right. This is the representation, that is the discrete Fourier series representation of your periodic signal. Okay. So, now what I have to do is I have to find these coefficients Cn. These are the coefficients, and we also know each Cn is basically 1 over t, where t is the period times 0 to capital T AC e to the power of j beta sine e to the, or for a general baseband signal, this is simply your SBT e to the power of, well, minus j 2 pi n FMT, okay, the nth frequency coefficient, that is Cn, nth coefficient of the discrete Fourier series, which is 1 over t 0 to t SBT AC e to the power of j beta sine 2 pi FMT times e to the power of minus j n FMT dt, which is basically 1 over t 0 to t AC e to the power of j beta sine 2 pi e to the power of, well, let us now use, well, I can write this as j beta sine 2 pi FMT minus j beta minus FMT into dt. Now, let us employ a substitution. I can employ the substitution 2 pi FMT equal to x, which means that dt becomes dx by 2 pi fm, and therefore, this integral for Cn will become Cn equals, well, substitute 1 over t, limit becomes 0 and well, x equals 2 pi fm t or 2 pi fm. So, the upper limit will be 2 pi fm times capital T, but fm equals 1 by t. So, this is simply 2 pi AC e to the power of j beta sine 2 pi fm t will be 2 pi fm equals sine 2 pi fm t, 2 pi fm t is x. So, this is simply j sine beta x minus 2 pi fm t, so is x. So, this is simply minus nx times dt is dx by 2 pi fm. Of course, t into fm, remember t is 1 over fm. So, t into fm equals, we have t into fm equals 1, and therefore, this will be your, well, 1 over t into fm becomes 1. So, this will be 1 or simply 1 over 2 pi 0 to 2 pi 0 to 2 pi e to the power of j beta sin x minus nx dx, that will be your Cn. That will be your Cn, and you can see this is basically your Cn. This is basically, in fact, I have an AC also, and this integral, now you can see I can write this, let me just write this as, well, AC into 1 over 2 pi integral 0 to 2 pi e to the power of j beta sin x minus nx, and now you can see this is a standard integral. This is basically the Bessel function. This is basically j n of beta. This is the nth order. This is the Bessel function of the first kind. This is the Bessel function where you are, this is a standard mathematical function. This is the Bessel function of first kind and order n. So, this is basically your Bessel function of the first kind and order n, which means your Cn, basically what we have shown is that your Cn equals AC times Jn beta. So, this is what we are able to show, that is, this is the nth coefficient of the discrete Fourier series. This is, remember what is this? This is the nth coefficient in the discrete Fourier series, but not of the FM signal, the discrete Fourier series of the complex baseband equivalent signal of the passband signal. Okay. So, this is the nth coefficient of the discrete Fourier series SBT equals AC e to the power of j beta sin 2 pi FM t. Okay. So, this is the nth coefficient of the discrete Fourier series. This is the nth coefficient of the discrete Fourier series. Okay. Now, therefore, I have Cn equals AC j and beta. Now, I have, therefore, I can write the expression for j beta sin 2 pi FM t. This is going to be, well, we have already seen this is your summation n equal to minus infinity into infinity Cn e raised to power of j 2 pi n FM t j 2 pi n FM t. Now, substitute for the expression of Cn. So, therefore, this becomes n equal to minus infinity to infinity. Well, that is Cn is AC j n beta e to the power of j 2 pi n FM t AC j This is basically the expression of the DFS of the discrete Fourier series of the complex baseband equivalent signal of the passband FM signal. Okay. Now, from this we can derive the passband signal. Remember, passband signal ST is nothing but the real part of, this is your SBT, complex equivalent baseband signal. So, the real part of SBT e to the power of j 2 pi FCT, which is basically the real part of, well, if I substitute this n equal to minus infinity to infinity AC j n beta e to the power of j 2 pi n FM t times this whole thing times e to the power of j e to the power of j 2 pi FCT which is equal to, now taking e to the power of j 2 pi FCT inside, this is simply real part of n equal to minus infinity to infinity AC j n beta e to the power of j 2 pi, well, e to the power of j 2 pi FC plus n FM t, which is now simply basically, if you take the real part of this, that is simply, now you can see real part of e to the power of j 2 pi FC plus n FM t is simply cosine 2 pi FC plus n FM t. So, this is simply summation n equal to minus infinity to infinity AC j n beta cosine 2 pi fc or 2 pi into fc plus nfmt. That is your ST, which is your pass band signal. So, this is your pass band signal ST, and remember the expression for ST is basically ST, remember, is simply AC cosine 2 pi FCT plus beta sine 2 pi FMT. So, this is basically summation n equal to minus infinity to infinity AC j n beta cosine 2 pi FC plus n FMT. Now, we know each cosine of 2 pi, that is, we know that this Fourier transform of cosine 2 pi f naught t has Fourier transform impulse of amplitude half at f minus f naught plus half delta f plus f naught. Therefore, each cosine 2 pi f c plus n f m basically is one impulse. If you take the spectrum of that, that is half impulse of amplitude half at f c plus n f m and impulse of amplitude half at minus f c minus f m. Therefore, now if you look at S t, let me rewrite S t again. S t equals summation n equals minus infinity to infinity A c j n beta cosine 2 pi f c plus f c plus n f m into t, a cosine 2 pi f c plus n f m into t, and now each of this cosine term has Fourier transform half delta f minus f c minus f m, that is half delta f minus f naught plus half delta f plus f c plus f m, which implies that the Fourier transform of S t. Therefore, now I have simply have to substitute the Fourier transform of the cosine, that is basically summation A c j n beta, that is half or A c j n beta into, well, delta or half, you can say half right here, half delta f minus f c minus n f m plus half delta f plus f c plus n f m. So, this is the Fourier transform of the, you are finally we are able to derive the Fourier transform of the, we are able to derive the Fourier transform of the pass band FM signal. What is this? This is the Fourier transform of the pass band FM signal, and you realize that it depends on this new function that we have seen. This is the Bessel function, J and B Bessel function of order n. This is the Bessel function of order n. Okay, so this is your Bessel function of order n. Okay, so this is the spectrum of this, and naturally, therefore, it depends on j and beta. Naturally, of course, this is all the is going from n equal to minus infinity to n equal to infinity, but obviously since we have to in practice we have to limit the bandwidth or spectrum of this transmitted FM signal, we have to choose a realistic value of bandwidth. So, a realistic value of bandwidth for this signal is the range of frequencies for which this quantity j and beta is significant. Okay. So, that is also another thing that can be noted, a realistic value of the bandwidth. So, although j n goes from minus infinity to infinity, although n belongs to minus infinity to infinity, a realistic value of bandwidth of FM signal is those j and beta for which is those frequencies, that is Fc plus NFM, for which j and beta is significant. Right. So, we have to choose an appropriate range of n or an appropriate range of these frequencies, right, for which j and beta is significant, that captures most of the signal power, most of the passband FM signal power. Okay. So, that gives us an estimate or a measure of the bandwidth of this FM signal, and then once we get the estimate of the bandwidth of this FM signal, then we can calculate various other aspects, alright, various other quantities. Okay. So, that is what we have. So, what we have now is basically we have considered a passband FM signal, we have derived its the expression for its spectrum. Now, we have seen that this spectrum literally spans from, I mean if you look at it analytically or the precise mathematical expression, it spans from over the entire frequency band. Alright. So, realistically we have to come up with a practical limit for the transmit bandwidth or a practical way to characterize a practical and meaningful how do you put it, measure to characterize the spectrum of this FM signal, and that is given, and that is something that we will look at in the subsequent modules, that is out of this spectrum how can we extract what is a practically feasible bandwidth or a practically good measure of the bandwidth of this FM system, right. So, we will stop here and look at other aspects in the subsequent modules. Thank you.